Okay, by the way, our acoustic music was from New Orleans premier Celtic folk group, the Poor Clares, from their Resurrected Lover album. And let's go ahead and take one more trip down to the real abyss. I guess this class is just getting absolutely abysmal. Okay. All right. You can define zones in the ocean by how much light you've got. The so-called photic zone goes down to about 200 meters, and that is about as deep down as you can go and still have some photosynthesis going on. That closely corresponds with a zone that's defined on the basis of wave and current activity, the so-called mixed layer. Within the mixed layer, water is kept on the move by wave action and by current activity. This is where the currents are happening and where winds are pushing up the water into waves. So the epipelagic zone is defined in terms of light, but it's pretty close to the same thing as the mixed layer. And that affects how much oxygen you get as well as how much light you get. Below it, things get a lot less interesting once you're down in the mesopelagic zone, otherwise known as the twilight zone. There's a tiny amount of light, but it's not enough for photosynthesis, so you don't get algae down here. You also don't get oxygen. The water is no longer getting stirred up by the influence of waves or by current activity, and the temperature falls off rapidly. It starts getting a lot colder a lot faster, and that shift in temperature, that temperature gradient, is called the thermocline, and we'll look at that in just a bit. Once you're down below about 1,000 meters, you are in the bathypelagic zone, aka the midnight zone, and there is absolutely no light. It's dark as the inside of a dead cow. Get even farther down and below about 4,000 meters, you are in the abyssopelagic zone. Get down even deeper than that, down into the bottom of the deepest trenches in the ocean, and you are in the hadopelagic zone. So here's pretty typical life in each of these zones. Up in the photic zone, you have jellyfish and Portuguese man-o-war, sharks and tuna and sea turtles and things like that, and an entire food web that's ultimately dependent on the phytoplankton, right? The floating little single-celled algae and things that we talked about. Down in the twilight zone, a lot of the critters that feed there actually dive into it and then come back up. So things like sperm whales and beaked whales, for example, are air-breathing mammals, but they'll take a big lungful of air at the surface and then dive down for an extended period of time and then come back up to breathe. Below that, down in the aphotic zone, where there's no light whatsoever, with the exception of bioluminescence, light that's generated by living organisms. So things like anglerfish and lanternfish and things like that. But other than that, it's completely dark except for bioluminescence. And as we discussed, in the open ocean, light can penetrate up to 200 meters. Light penetrates a lot less in coastal waters because those tend to have more sediment. They tend to be murkier. But at least green and blue light wavelengths can penetrate down 200 meters. Red, of course, is stopped a long time before you get down that deep. And remember that the relationship between depth and temperature is called the thermocline. And this is what the thermocline looks like in the tropics. Water at the surface may be close to room temperature, nice, good swimming water. And ultimately, what's heating that water is, of course, the sun. The effects of currents and waves tend to spread that heat through the upper few hundred meters. That's called the mixed layer, and it is not quite the same, but very close to that photic zone. They overlap quite a bit. Once you get below that, the temperature starts falling off dramatically. It gets a lot colder with depth. And once you're down below about 1,500 meters, you're down to about 5 degrees Celsius, and slowly getting colder and colder as you go down. Obviously, where the surface ocean is very cold to begin with, like the polar ocean, there may not be any thermocline at all, but there's certainly a pronounced one in the tropical areas. So life living at great depth has the problem of how do you cope with very cold temperatures? That tends to slow everybody's metabolism down. For the same reason, you have less oxygen once you get out of the mixed layer. So that's dissolved oxygen concentration. What you're looking at is 180 degrees east is that's the international date line that cuts right across the Pacific Ocean. And on the x-axis, you've got latitude from 90 degrees north over on the right, which is positive, to 90 degrees south on the left, which is negative. And that white area at the bottom is a very rough diagram of the contours of the ocean floor. So that big white area at the left, that represents Antarctica. That white area up at about 70, 75 north, that would be Siberia. And the little zigzags that don't quite reach the top are undersea mountains, probably some ridges and things like that. Anyway, the graph you're looking at shows you dissolved oxygen, and the warm colors, the reds and the oranges, there's the greatest amount of oxygen, and you can see it's pretty high at the surface because oxygen is diffusing into the ocean from the atmosphere. And then currents, of course, are spreading it around. Below that mixed layer, once you get down below about 500 meters, remember what's happening is that marine snow is constantly raining down from the photic zone, right? All of the dead algae and fecal pellets and everything else. And that stuff decays as it falls. Because there are decay bacteria and things like that on it, and decay consumes oxygen. So below that mixed layer, you start getting much lower oxygen levels. Most of that decay happens in the upper 1,000 meters. So between roughly about 500 and 1,000, you can really see that in the northern hemisphere between 0 and 60, you have this oxygen minimum zone. So no oxygen, and it's really cold, and there's no light. So as adaptations to that, everything in that oxygen minimum layer tends to be very, very slow. Organisms drift. They don't use their muscles very much. If they do, they often move very slowly. They'll often, if they feed, if they're feeding on the marine snow, they'll often try to trap it passively instead of actively hunting anything. So this is a great example. One of these days I'm going to go as one of these for Halloween. it's not actually that big. It's only a few inches long. Some of the pictures of marine critters that you see look like hideous monsters, and you have to remember that they're not actually that big. But this critter, Vampiroteuthis infernalis, literally means vampire squid from hell, because of its red color and generally eerie appearance with that webbing in between its arms, somewhat resembling a vampire's cape. But you don't need to be afraid of it because it's an extremely slow swimmer. Those flaps on its head slowly flap back and forth. The thing looks a little bit like an extremely sluggish version of Dumbo, and enable it to swim, but mostly it just kind of drifts. And again, this is all adaptation for life in very cold, low oxygen waters. You also get a lot of jellyfish down here. This is one of the most abundant animals in the world, Paraphila, affectionately known as the helmet jellyfish. Through the transparent bell, you see that bright red thing that looks like a pointy helmet sticking up. That's actually the critter's stomach. Jellyfish have a low demand for oxygen because the body is something like 99% water. And because they're nearly neutrally buoyant, they can do a lot of drifting. They don't have to exert themselves very much. So you get jellyfish in some quantity once you're down in the twilight zone. And you get the same thing with critters called deep sea siphonophores. I think I talked about things like the Portuguese man-o'-war, which is not a jellyfish. It's actually a colony of animals. It's not a single animal at all. And different individuals in the colony are specialized for different things. So you have some individuals that do the reproducing, and some that do the feeding, and some that do the defense, and some that swim or float. There's lots of siphonophores in the deep sea, many of them very poorly understood or not even known until we got to where we could start sending probes with cameras down there. These are, even if these do wash up on shore, they're generally just completely shredded. They're so delicate. So we knew very little about these guys until the advent of deep sea cameras. And so this one right here, if you can see, there's this very long strand of individuals. Looks a little bit like a fringe or a comb. Each one of those little teeth on the comb is an individual. They're strung out like that, all growing from a common stem. And some of them have extremely long extensions that are hanging down. Essentially, this is a living drift net. They mostly rely on neutral buoyancy. They can't swim very fast. And it's a very low energy lifestyle. And they'll just wait for something to drift into one of those long string-like tentacles that are well armed with stinging cells. So again, this kind of lifestyle is an adaptation to conditions in the mesopelagic zone. Ditto for this thing. This is the big fin squid, and it has these huge fins on either side of its head, and it can move by flapping them, although it flaps them very slowly. And the tentacles have this right angle bend in them. They stick out straight from the head, and then take this 90-degree bend and start hanging down. And this is another very slow, steady swimmer. It's a reasonable guess that it might use those long tentacles also kind of like drift net fishing, just waiting for something to blunder into them. But we know very little about big fin squid. They've rarely been seen alive. So there's not many critters that are adapted to live in that mesopelagic zone, but there are plenty that visit. This is a beaked whale. Toothed whales include things like dolphins, sperm whales, and orcas. And then baleen whales, we talked about a bit. They have no teeth, but they have these filtering structures in their mouths called baleen. Beaked whales are a subgroup of the toothed whales, and we really don't know very much about them. There are several species that weren't even discovered until the 20th century. They spend a great deal of their time at great depth, way out away from anything else, so they're not easy to observe. You have to be kind of lucky to see one broaching the surface to breathe, which is what this one is doing right here. What was it? They were actually in the news, though, a few years ago when dead ones started washing up on beaches, and it seems to be connected to some kind of either weapon or powerful sonar system that the Navy was testing at the time. So, yeah, that's a potential threat. Anyway, beaked whales regularly dive below 500 meters. The record I could find was nearly 3,000 meters. There's a typo in there that should say taking over 2 hours per dive. As far as I know, this is the record deep dive for an air-breathing mammal. Oh, if anybody's curious, the record deep dive for a human was done by this crazy guy from, I think, Austria that actually managed to get down nearly 300 meters, maybe like 250 meters or about 850 feet. And unfortunately, he suffered some damage on the way up because of something called decompression sickness. So yeah, most people can't do that. Sperm whales also do this, and they specialize in mesopelagic squid. Called that, by the way, because an awful lot of that head is filled with oil. That head's filled with an organ that's called the melon because it looks like a giant watermelon. It's loaded with oil, and that oil used to be burned in lamps. There's a famous cartoon I wish I'd included of a bunch of sperm whales dressed up in tuxedos, drinking champagne and clinking their glasses at the discovery of petroleum in Pennsylvania back in the 19th century, because it was the discovery of crude oil reserves, the ability to drill for them, and the ability to process them that created fuel that could be burned without having to go out and kill a bunch of whales to get it. And that kind of put an end to the whaling industry. Anyway, these folks can reach 2,250 meters down, and they feed on mesopelagic squid like this Humboldt squid down there. They've got well-developed eyes. They're excellent echolocators. That melon actually enables them to send out and receive focused beams of sound. It's very adaptive for precision echolocation. They can probably spot bioluminescence as well. And they feed a lot on squid. I've seen sperm whale skin that's got markings of squid suckers on it. So evidently they have some pretty serious fights with giant squid. We talked about bioluminescence. If you're down in the twilight zone, squid and fish may actually use counter-illumination. There's just enough light coming from above, not enough for photosynthesis, but just enough that it might be possible for a predator coming from below to see an organism's silhouette against the light coming in from above. And to counter that, there are critters that can generate light on the ventral side to match the amount of light that's coming in from above. So this is what a bioluminescent squid looks like from below. Probably would not look like that if you could actually go down there. The film this was taken from is probably more sensitive than your average retina is. But yeah, it's thought that these can tune the amount of light that they're generating to match conditions in the environment where they live. World War II is, I guess, the first major, no, there were submarines in World War I, but World War II, you've got major submarine warfare. And submarines, of course, navigate by sonar, sending out sound pulses and listening for the echoes. And sonar operators noticed that operating in the Pacific, during the day, they'd get sound waves reflecting off what looked like the bottom of the ocean between 300 and 500 meters down. So at the very base of the mixed layer. But then that would disappear during the day. And this is in places where the real bottom would be known to be, 8,000 meters down. And then there's this false bottom that appears during the daytime, much more shallow. It turns out that this is caused by sonar reflecting off the swim bladders of mesopelagic fish. There are extremely abundant fish in that mesopelagic zone, so abundant that sonar can actually make the schools of mesopelagic fish seem like the bottom of the ocean. Lanternfish feed at night on plankton. They'll do this diel migration thing that we've talked about earlier, where they'll rise into the epipelagic zone to feed on plankton and then retreat by day into the dark. I am assuming because predators don't have a really easy time in the mesopelagic zone with no oxygen and almost no light. And this is one of them. This is one of over 200 species of lanternfish, and you can see why they're called that. Those electric blue spots on the body are bioluminescent. Different species have different arrangement of spots, and I don't know, but I would guess that this is a way for the sexes to find each other. That males of one species can find females of the same species by responding to particular arrangements of spots. Just like birds and lizards on land can identify each other with specific color displays. I don't absolutely know. That would be interesting to study. But there you have it. Even more abundant than lanternfish are the bristlemouths. It's estimated that bristlemouths are the most abundant vertebrate in the world. At any given time, there are hundreds of trillions of individuals. That's 10 to the 14 individuals in the world at any given moment. So there goes a bristlemouth. That's why they're called that. You can see the extremely narrow teeth. And then mesopelagic fish that don't migrate vertically, like this one, have no swim bladder. If they're not, remember that the amount of gas in the swim bladder enables a fish to rise or to sink. The fish can regulate its own buoyancy. And if you're not going to migrate up and down, you don't need a swim bladder. And these have very weak bones, weak muscles, and a great deal of jello making up the bodies. And again, weak muscle, don't need strong muscles if you don't have oxygen to run them. Gelatinous material means these probably rely on neutral buoyancy more than anything else. And that's what I've got for you today. All right, that one ended up going a little bit short. And I'll go ahead and stop recording.